Mount a dial indicator on the machine base or the machine component and place the plunger of the dial indicator on the shaft with it pointing to the shaft center line. Be sure the plunger is depressed about halfway to ensure good contact at all times. Zero the dial indicator and rotate the shaft watching the dial indicator through its full swing. Repeat the procedure on each coupling hub. This technique can be used to determine whether the coupling was bored askew, whether it was bored off-center, or whether the shaft is bent. Any of these conditions require corrective work. If the coupling runout is greater than 5 mils, replace it. It is especially critical to have a true coupling when using the face rim alignment method. Soft foot is the condition where one or more feet are not on the same plane with the others. It can also be when feet do not rest flat or solidly along the surfaces. The actual machine feet could be true, but if the base is not true so that the feet do not sit squarely on the base, then the effect is the same and is still called a soft foot condition. When a soft foot is tightened down, it pulls on the machine and can warp or distort the machine casing, causing a bind on the rotor and preloading the bearings and seals, creating improper internal clearances and increased vibration. This soft foot condition decreases machinery life and causes even the most skilled craftsmen to chase their tail during the alignment process. Check all machine feet, correcting the soft foot, and the machine will run better, and you will have an easier job of aligning to tolerances. The soft foot may be one that is bent down, bent up, or parallel to the base, but not touching. The soft foot could even be due to an untrue base plate. To check for soft foot, make sure all the hold-down bolts on the feet are loose. This is where science becomes an art. Use a feeler gauge to measure the clearance under each foot, increasing the thickness until the feeler gauge fits firmly under the corner of the foot. Record this measurement for this corner of the foot and continue measuring each corner of the foot to determine the profile of the clearance. After the measurements have been recorded for each of the 4 corners of the foot, cut shim stock to fit the profile. Where one side is thicker, use 2 or more layers of various thicknesses of shim stock. Depending on the measured clearances, the shims may need to be square, C-shaped, L-shaped, a straight strip, or any combination to create a customized wedge. Remember to sandwich the thinner shims between the thicker ones. Using needle nose pliers, insert the shims under the foot and check the clearance again with a feeler gauge. If the clearance is 2 mils or less under the entire surface, then move to the next foot and repeat the process. This must be done for each foot to correct the soft foot condition. If the machine component to be aligned is a pump, compressor, or turbine, then check for piping strain. Piping strain is any condition when the pipe flanges do not freely make a perfect match, but must be forced into a perfect match by some means. This forced match distorts and weakens both the pipe and the pump. The pump casing is pulled, causing flexing which moves bearing locations, bending the shaft. So a pump motor combination can be in perfect alignment, but connecting ill-fitting piping can force it into a misaligned condition. To check for piping strain, make sure all feet are tightened to the correct torque. Then set up 2 dial indicators on the coupling end of the pump bearing, one in the horizontal position and one in the vertical position. These dial indicators should be mounted on the base so that they are independent of machine movement. This means the one for the vertical reading will probably be reading the bottom of the shaft due to the short length of the mounting brackets. To zero and check this dial, use a small mirror to read it. After the dial indicators are in place and set to 0, loosen the piping flange and read the dial indicators again. If the movement is more than 2 mils, correct the piping strain. Expansion joints can be used in the pipe length and are designed to absorb thermal growth and can withstand some small amounts of misalignment. However, they can only correct for so much misalignment and should not be used in extreme cases of pipe flange misalignment. In extreme cases, a customized pipe filler ring called a Dutchman may be installed. This ring should be custom made to correct for both angular and offset misalignment of the flange. There are arguments about which to perform first, the alignment or attach the piping. If piping strain corrections are made properly, it should not matter. One consideration that is often overlooked in the alignment process is bar sag. Anytime dial indicators are used for the alignment process, there will be some amount of deflection of the bar due to gravitational force. When the shaft is rotated, the bar sag varies and must be measured and accounted for in the alignment process, or all the calculations will be in error. To measure bar sag, extend the bar to the length it will be used during the alignment process and mount it onto a mandrel or straight section of pipe. It should be mounted exactly as it will be used on the machine, including the bolt torque. Be sure the pipe is of sufficient size and wall thickness that it does not sag itself. Position the dial indicator to the top and zero the dial. Rotate the shaft to the bottom and read the dial. It will be a negative number equal to twice the distance of the bar sag. There is sag while the bar is positioned at the top. However, we zeroed the dial indicator as if there was no sag. So the reading at the bottom is twice the actual bar sag. This amount must be compensated for when performing the actual alignment. When the bar is rotated to the 90-degree position or the 270-degree position, the dial should read half the bottom reading so that they sum to the bottom reading. Remember that this bar sag must be determined prior to the alignment job and must be compensated for in the vertical readings of the face rim method and the reverse dial methods. However, when CSI's Model 8110 alignment fixtures are used in conjunction with the UltraSpec 8000 alignment analyzer, a patented method is used for determining the total bracket sag after the brackets are mounted on the machine. Remember to perform all these pre-alignment checks before the actual alignment. First, inspect rotating parts for wear. Measure the shaft and coupling runout. Clean the machine feet and base plate. Check condition of shims. Check for soft foot. Check for piping strain and measure bar sag if applicable. Now, we are ready to perform the alignment. Earlier, we reviewed the alignment methods and noted the differences among the methods. Although they seemed very different, they all have the same three steps. First, measure the misalignment, and next, make calculations, and then adjust the machine. Even Bo and Boo performed the same steps.
Last time I had a job like this, it took me 2 Pepsi cans. Hey, Boo, give me 2 Pepsi.
I don't have 2 Pepsis, but I got a Pepsi and a Mountain Dew.
Although the same basic steps are required for each alignment method, the tools to measure and calculate the moves vary greatly. Tools for moving the machine vary nearly as much. It is the preciseness of the measuring, calculating, and moving that makes the difference in the alignment job. We will first look at the reverse dial indicator method, and then the electromechanical system, and finally the laser setup. All the alignment methods require accurate documentation so that the alignment could be set up again to save time. The documentation should include the name of the person performing the alignment, the results of the inspection, the soft foot corrections made, any piping strain and corrections, the amount of thermal growth, the orientation of the machine, that is, which is the left and right side, and the machine dimensions. Since the corrective moves are calculated for the foot locations, accurate dimensions must be recorded. Measurements must include the distance from the center of the hub to the dial location, from the dial location to the bolts on the inboard feet, and the distance between feet. These measurements should be accurate within 1/8 inch. For the reverse dial method, mount one indicator bracket on the shaft or coupling hub with its dial indicator resting on the opposite shaft or coupling hub. Be sure to mount it so the plunger is pushed in about halfway. The plunger must have some amount of pressure on it during a full 360-degree swing of the shaft. In severe misalignment, the plunger may either ride away from the shaft or bottom out. Either case will generate invalid data. The second dial indicator is mounted in the same way as the first. Rotate one to the top or 12 o'clock position and zero the dial. To check that readings will be accurate, rotate the shaft to the 3 o'clock position and record the dial reading, being sure to note whether it is positive or negative. Rotate the dial to the bottom and record its reading. Continue rotating the shaft to the 9 o'clock position and record the number. To check that the measurements are valid, a rule of thumb can be used that the two side readings should total to the bottom reading. If the bottom reading is minus 15 mils, the side readings could be any numbers that will sum to that, such as minus 8 and minus 7, or minus 17 and plus 2. If the data validity rule indicates bad data, then there is a mechanical problem or the plunger on the dial could have bottomed out. Piping strain, soft foot, and a loose coupling will cause the validity rule to be off. Correct the mechanical problems before continuing. If you are using the graphical method for calculating the moves, be sure to compensate for bar or bracket sag. Use the values determined for the bar sag and subtract them from the bottom or 6 o'clock reading. A good method to calculate the machine moves is the formula method. This method is based on selecting one machine as stationary and the other as movable. The formula for the move is 1/2 the quantity of M1 plus M2 times the leg over the spacing minus M1, where M1 is the reading at the stationary machine and M2 is the reading at the movable machine. The leg is the distance from the location of the stationary machine reading to the leg to be moved, and the spacing is the center-to-center distance of the dial indicator brackets. This formula calculates the move for one leg plane in one direction only. This means the formula must be used 4 times for the complete machine move. Draw the machine noting the measurements. Since we must solve for either the inboard legs or outboard legs separately, we will label their respective distances L1 and L2. Let's use 6 inches as the spacing in this example and solve for the vertical move for the inboard foot. First, normalize the readings by subtracting a number from both sides that will leave one of them 0. The vertical readings are already normalized because the top is 0, but remember to subtract the bar sag from the vertical reading. Now plug in the numbers to solve for the vertical move for L1. M1 is 27, M2 is 0, L1 is 24, and the spacing is 6. M1 again is 27. This gives us a number of 81 divided by 2, which is 40.5 mils. Since the number is positive, the leg must be moved up 40.5 mils. Repeat the steps, solving for the vertical move of the outboard feet and the horizontal moves at each set of feet. When moving the machine in a horizontal position, set up dial indicators at each foot that will be moved, being sure to set them to 0. As you push the machine with the jack bolts, watch the dial indicators and move the machine the calculated distance. If no jack screws are available, temporary jack bolts may be mounted on the nuts of hold-down bolts to move the machine horizontally. When the machine has moved the calculated amount, torque the hold-down bolts and take another set of readings. Repeat the steps until the machine is within tolerances. In the electromechanical system, the indicators are the digital indicators and are referred to as heads. These electronic heads transfer data measurements from the 4 90-degree positions to an alignment analyzer, which then calculates the moves for each foot. The brackets for attaching the heads must be mounted to the shaft or coupling and require a surface of at least 3/4 inches wide. The farther apart these heads are spaced, the more accurate the calculations will be. Mount and level one bracket, then mount the other bracket, being sure to level it also. It is best that the brackets are in the same plane. Then mount the heads on the brackets, positioning the stems and bars to ride on the plunger of the opposite digital indicator. The benefits of an electromechanical system are more than just time-saving. It measures bar sag with the heads and bars installed, therefore eliminating that pre-alignment check. It reduces error from reading dials by digitally measuring the movement and transferring it to the alignment analyzer, which calculates the moves. If the machine is not coupled, position it axially before making any measurements. Distances between feet and from the feet to the face of the heads are required for accurate calculations. The most critical distance, though, is the distance between the faces of the heads. All these measurements need to be as accurate as possible, so it may be necessary to use a plumb bob to measure the distance from a foot to the face most accurately. The distance between the faces should be within 1/16 of an inch, and all other dimensions should be within 1/8 of an inch. Enter all of these dimensions into the analyzer. Be sure the feet are torqued to the required amount before making your readings. One benefit of the electromechanical system is that it doesn't require a full 360-degree swing in order to calculate the machine moves. At least 3 readings are required, so a minimum rotation is 180 degrees. The 4th value is then calculated from the data validity rule. Be sure the heads are in the on position and zero them at the top or 12 o'clock position. Rotate the shaft slowly, stopping at the left, right, top, and bottom positions. In the analyzer, view the data and the recommended vertical moves. The vertical moves should be made first because it often affects the horizontal moves. The analyzer calculates 6 potential solutions that will correct the misalignment. Toggle through them and select the one that will be the simplest to perform. And if the machine is not within tolerances, add or remove shims to make the required adjustments. The horizontal moves can be displayed in the same way as the vertical moves. Toggle through them and select the one that will be simplest to perform. Use jack screws to position the machine while monitoring the analyzer's live mode until the machine move is complete. If the machine does not move, it may be bolt bound. That is, the bolt is already against the foot and cannot move. Torque all bolts and collect another set of readings to check the work. The job is seldom within tolerances with the first move, but usually requires 2 or more moves to bring it within tolerances. Continue making measurements and moving the machine until it is within tolerances. The laser system setup is very similar to the electromechanical system. Mount the brackets in the same way. The laser heads are different than the electromechanical heads in that they use wireless communication through 3 infrared ports to talk to the analyzer. 2 ports are on the sides and 1 port is on top. Each head has a visible laser beam and target. Before any data can be processed, the machine must be rough aligned so that the beams hit the target during the entire shaft rotation. Adjust the screws until the laser beam strikes at or near the center of the target. Rotate the shaft and check to see that the beam stays on the target during the rotation. If it does not, move the machine until a rough alignment is achieved. After the laser heads have been set up, define the alignment job in the analyzer and enter the data required. The data requested includes the machine type and each component type for the machine, as well as specifying the direction of rotation, the shaft turning speed, the laser orientation, the thermal growth data, and the dimensions of the machine. Steps and calculations are available for identifying soft foot problems. The laser system has 5 methods for measuring that may be selected from. They vary from the totally automatic, where all you do is turn the shaft and the analyzer accepts the readings, to the interactive manual, which lets you be in charge of accepting the readings. The partial sweep is a helpful tool that calculates the machine moves when the shaft rotation is limited. At least a 90-degree sweep is required to make the calculations. The principle used is a patented curve fit, where up to 36 points are measured during the sweep and are plotted to achieve a sine wave curve. Data is extracted from the sine wave to calculate possible machine moves. Another benefit of the partial sweep is it can identify other machine problems such as shaft bind, looseness, and piping strain. After the measurements are collected, display the vertical move solutions. Select one and make the machine moves. When the vertical move is complete, select the horizontal move. Then toggle through the possible solutions to the best move. The alignment analyzer can be set in the live mode while adjustments are made. Movements are displayed and updated on the screen to let you see the status of the machine move. The heads compensate for any horizontal shifting from the vertical move and display the updated horizontal solution when the live mode is selected. Torque the bolts to the required amount and take another set of measurements to evaluate the current shaft positions and check against tolerances. Repeat the procedure until you are within the tolerances. The screen shows the tolerances for this machine with the area under the smallest curve being the excellent range. This curve is defined by a CSI tolerance chart. Since every misalignment can be broken into an amount of pure offset and pure angular misalignment, they are listed here in excellent and acceptable ranges for the various machine speeds. The angular misalignment is measured in mils per inch. For every inch of shaft length, that is the maximum allowable angular misalignment. Offset misalignment is measured at the center of the coupling in mils only because it is parallel and will be the same distance off-center its entire length. The plotted tolerance chart indicates that for a machine in this speed range, a pure angle misalignment of 0.45 mils per inch is very acceptable, and that a pure offset misalignment of 2.5 mils is well within the acceptable limits. However, a combination of the two misalignments puts the point of intersection clearly outside of any tolerance limit. For this reason, CSI recommends plotting angular and offset misalignment together when establishing specified tolerances. Use the recommended tolerances of the machinery components being aligned, that is, motor, pump, and so on. If no tolerances are available, use the tolerances provided by CSI. We do not recommend that coupling tolerances be used. For example, one coupling manufacturer accepts 4 degrees of misalignment per inch of shaft length. This seems reasonable. However, 1 degree is equivalent to 17.5 mils per inch. So 4 degrees is equivalent to 70 mils per inch. As stated earlier, the coupling may withstand this amount of misalignment, but the forces are still transferred to the machine, damaging bearings and other machinery components. When the tolerance chart indicates the machine is well within the limits, then store the job in the analyzer. Remove the brackets, install the coupling guard, and follow the safety procedures to button up the machine. Remove your lockout and restart. When the unit returns to a steady state condition, follow up with vibration measurements, temperature measurements at the coupling, and recheck the data used as a basis for calculating the thermal growth. Another follow-up is to recheck the alignment in 6 months, and if it is within tolerances, recheck it once a year. This is made easier with the laser and electromechanical systems because the alignment job can be stored in a computer database where it can be reloaded into the alignment analyzer at a later date. This speeds up the alignment process. Now only the machine distances and any new thermal growth information is required before measurements are taken.